Welcome back. I'm Steve Miller. We're now on lecture 4 of the linear regression unit. And what I want to talk about is one of my favorite problems, the GermanTank problem. And this is a terrific example of many of the key concepts in mathematics and statistics. And if you want to talk about real-world applications, this is one of the best. So the figure on the left is Europe before the start of major hostilities. So this is right before the invasion of Poland. And the next is less than 2 years later. It's Europe in 1942, maybe a little bit more than 2 years later. And you can see the incredible advance of the German forces. You can see them driving deep into the Soviet Union. You can see them driving into Scandinavia. You can see them taking France and getting into Italy. And so the question is, how were the Germans able to advance so fast so quickly? And a lot of it was they had terrific tank tactics. They had terrific battlefield tactics. And it was very important for the Allies to understand not just what their tactics were, but what were the resources Germany had, and what resources would the Allies need to stop them. When you only have finitely many resources, you have to decide, well, where do I deploy my forces? How many forces do I need to put in this theater of battle versus another? So this was an extremely important problem for the Allies. So they wanted to know how many tanks were the Germans producing and how many were they sending to various theaters of battle. So how can you find the number of tanks? Well, one solution, of course, is to just ask. But given that the two sides are at war, it is extremely unlikely that the other side would answer a question like that. Now, you could use spies. The British had broken a lot of German codes. So perhaps you could intercept things like that. Or you could also have human agents on the ground. It turns out that there's another way, mathematics and statistics. And given that this is a data science class, it's probably not going to be too surprising to you that I'm going to talk about the mathematician and statistician's contributions to this problem. So this is the original formulation of the GermanTank problem. After battle, you see some serial numbers S1, S2, all the way up to SK on captured and destroyed tanks. And you want to figure out how many tanks were produced or how many tanks are in the theater of battle. So we're going to assume in the original version that the tanks are labeled sequentially. They're labeled in order, starting at 1 and going up to some unknown n. The more general problem is you do not know what the starting value is, but it turns out you can handle that without too much trouble. And the even more general problem is that the serial numbers are encoded, they're encrypted, and so they're all over the place, they're not in order. A lot of things nowadays encrypt serial numbers like this, so people do not know exactly how much has been produced. You may not want a customer to know that they are your very first sale and they're buying product number 1, for instance. You want them to think that you are a well-established company. So as remarked, the original formulation is the tanks are numbered from 1 to big N. We observe K tanks, so K is fixed, we observe some number. And then the largest seen is little m, and we want to estimate how many tanks there are given that we observed K tanks and the largest one was M. As I marked, the new version is when we don't know what the minimum value is. So the question is, can we come up with an idea of what the conjectured relationship should be between M, K, and the number of tanks produced? We can also gather data by doing some experiments, which you'll do on homework, and use that to try to figure out the relationships. Now, we've got to be extremely careful, because if we come up with the wrong answer, there are severe consequences. There's tremendous dangers in overestimating and underestimating. So one of my favorites is from President Lincoln in the US Civil War. And he remarked, if General McClellan isn't going to use his army, I'd like to borrow it for a time. So McClellan was famous for being great at training his army, but always being under the impression that he was greatly outnumbered in the field and he needed more reinforcements before he could attack. And so he squandered a tremendous number of opportunities to deal crippling blows to the South and possibly end the war much earlier. And so if you overestimate the enemy, it might be paralysis. You might not attack when you actually have things in your favor. If you underestimate the enemy, you have another problem. You might not send adequate forces to the battle and you might lose. So in this talk, I want to talk a little bit about some of the mathematical preliminaries. I'll move that to the theory one, which will be lecture 5. We'll talk about the original version of the German tank problem in a moment and how we can sniff out what the answer is. Talk a little bit about the new version, but not into too much detail, but if you want, I'm happy to share some theory on it. And then talk about how we can use regression to conjecture the right answer. So let's go back to the original version of the tank problem. So we want to figure out how should M hat, the best guess for the number of tanks produced, depend on M, the maximum tank number observed, and K, the number of tanks observed. So if you want, this is a good place to just pause for a few moments and think, how should it depend on M? If I increase M and keep K fixed, what should happen? If I increase K and keep M fixed, what should happen? So hit pause, think about it for a few minutes, and then hit resume. All right, welcome back. So the first is a really simple thing. We expect that the best prediction, it's going to be at least M, because the tanks are labeled sequentially from 1 to big N. If we observe the largest serial number of 15, we're clearly not going to guess that there were less than 15 tanks. It's going to be 15 plus something. So whenever you have a complicated problem, if there are some parts that you can extract out, that's wonderful. So we extract out the M, and it's going to be M plus some other function, G or MK. And the simplest guess is that it's equal to some constant times M divided by K. And if you think about this, well, if we observe a larger serial number, it makes sense that we would predict that there are more tanks. And the more tanks we observe, the less that we seem to need to inflate to get to the largest number. We'll go into this in great detail in a moment. So the actual answer is M times 1 plus 1 over K minus 1. And we'll show you in a few moments how to derive this theoretically. Whenever you see a formula, you want to ask, is it reasonable? Well, one way to see if it's reasonable is to look at some extreme cases. So if I take K equals 1, we only observe one tank. If I only observe one tank, my guess is it's probably somewhere in the middle, so it would probably be around N over 2. So if K equals 1, if we guess N is around N over 2, we would have N over 2 times 2 minus 1. Yeah, that's about N. That seems reasonable. The other extreme is imagine K equals N. Imagine we observe every single tank. Well, if we observe every single tank, then M has to equal N as well, and we would get N times 1 plus 1 over N minus 1, and when the dust settles, you get capital N back. So these are very reasonable. Now, what makes this problem challenging is the answer depends on both M and K. And depends on M divided by K. M and 1 over K multiply together. So it's going to be a complicated relationship, and this is going to cause some interesting complications. So to just end the first part, this is one of my favorite charts. It's from Wikipedia, source of all knowledge, fountain of all wisdom. And it has the statistical estimates from a couple of months. It has the intelligence estimates. And after the war, there's access to the German records as to how many tanks did they actually produce. And you can see the statistical estimates are off by a phenomenal amount. Off by factors ranging from 7 to maybe 5 to 7, off by a good amount. Whereas the mathematical and statistical estimates are pretty close. They are in the right order of magnitude. They are in the right ballpark. So what we saw in this lecture, lecture 4, is the beginnings of the German tank problem. This is a problem with tremendous real-world importance, trying to estimate how many tanks were being produced. We saw that it's reasonable to expect that there should be some relationship between the largest tank observed and the number of tanks observed and the number of tanks produced. And we led to a conjectured formula. And then we tested our conjectured formula on some extreme cases to see, is it reasonable? And it passed those Snell tests. And then in the next lecture, which is a supplemental advanced lecture, I'll go through the theory and show you how you can actually prove that this is true.